Hello, everyone. Congratulations on making it to the end of Unite here. Woo! All right. My name is Jonathan Chambers. I've been working at Unity for about 5.5 years, exclusively on scripting runtimes. That would be Mono, IL to CPP, the class libraries associated with that, dotnet tooling like the C# compiler. And one of the first things when I was hired that I looked into was actually upgrading the version of Mono we use. So it's kind of nice to finally be talking about that today, 5 years later. So let's dive right into it. So we're going to go through past, sort of present, and future. So the previous state of .NET and Unity until very recently was not a great one. We are using Mono 2.7 roughly, which is about 7 years old at this point. We've, of course, supplied patches and bug fixes and added features to that, but the core code base of the runtime in use in most places in Unity was 7 years old. That corresponds to .NET 3.5, and that's about C# 4, and that's, I think, Visual Studio 2005 era, so quite a long time ago. And not only are you constrained to C# 4 and using .NET 3.5, but increasingly in the .NET ecosystem, we're just being left behind. So newer libraries are being written. They're only writing them to be compatible with .NET 4.6 or C# 6, and using those libraries from Unity is becoming impossible. The pain you feel, we also feel as well. Unity developers are .NET developers. We have a very large amount of C# code. Many of our new features are majority C# or complete C#. So the pain you feel related to language features you can't use, class libraries you can't use, runtime features you can't use, we feel the exact same ones inside of Unity, and we want that to change too. In addition to being stuck on this old version of Mono, we also support a variety of scripting runtimes. So we support Mono, which I already mentioned. We support IL to CPP, which is a ahead-of-time runtime that we built ourselves that has a focus on portability and performance. So IL to CPP is a little bit different in that it takes your .NET code, converts it to C++, and compiles it with a native platform compiler. And then in addition, for our UWP platforms, we have a WinRT.NET Core-based scripting runtime. So we're supporting multiple runtimes at differing levels of compatibility. And then in addition, we have multiple versions of some of those runtimes. So we have an older version of Mono, which we're using many places. We have a new version of Mono now, which I'm talking about. But in addition to that, on some platforms, they have their own special version of Mono. So at any given release, we're probably supporting 5 or 6 different versions of a scripting runtime. So we want to leave this place and get to somewhere better. The last time a runtime upgrade happened for Mono was a really long time ago, and it doesn't inform much on what we want to do today. The closest analogy we have in recent times is rolling out the IL to CPP runtime. And we learned a number of things there. Of course, there's the 80-20 rule, which is more like 98-2, in the sense that a large portion of tests will be passing and applications working. But if you had a Venn diagram of everybody's application, there's 98% in the middle where everybody uses the same stuff, and then everybody has a different 2%. And 100% of applications working 98% is not nearly as good as 98% of applications working 100%. So we know there's a long tail to get everybody's applications working the way they want to when we make changes to the runtimes. There's performance characteristics that are hard bounds. One of the things we learned with IL to CPP is we were making design decisions, say on a memory allocator, and we might flavor performance over the actual memory usage at runtime. And we would trade a great performance gain for maybe 2 or 3% memory gain at runtime. And what we didn't realize at the time was a lot of people have hard stops. So a lot of people will build their applications using all the available RAM on the system, essentially, that their application can get a hold of. And we would bump that by a small amount, their application would get out of memory. Similar for, say, disk size. So the actual deployment size of your application, again, we might make some optimizations so that we could load faster. That might take another megabyte on disk or 2 megabytes on disk. And what we didn't realize at the time was, again, many people are trying to get under over-the-air limits, and they might be right up against the bounds. We make these small changes, and it has a drastic impact on their application. And finally, there's undefined behavior, which officially we don't support, but we try to make them match. So if you look at .NET runtime, something like static constructors. The static constructors on a C# class is defined to run before any access of static fields, static methods, or any object instances are created. But other than that, it's pretty wide open, which means we could just run them all at startup if we wanted to, right? But most people expect them to run immediately before their first access. And if we would run them in a slightly different order or a slightly different time, you would see odd behavior. Maybe someone in a static constructor writes a file to disk, and then somewhere else they assume that file exists with sort of an implicit relationship. So we encountered a lot of undefined behavior. So all these things come together to let us know that it's not easy when we make changes for your application to just work, but that is our goal. So the new runtime is being deployed with the following thoughts in mind. One is it's built in, so we don't do a special version or a special build that's including this. At 5.6, we did put a special build out that had a preview of this, but from 2017 onward, we'll see in a second, the scripting runtime upgrade is available in the editor, the Unity you download. It's just one checkbox in the player settings, and you can swap at the per project level into using the new runtime. Again, that's opt-in, so we're not forcing this on you anytime soon. The plan is to roll this out and let you opt in when it makes sense for you. And when it makes sense to drop the old one and what features we work on is driven by you. So as this first went out, we got feedback about the managed debugger. There was a lot of bugs coming in and feedback on the forums, people saying, I'm trying to use the new runtime, I want to look into something, and the debugger's not working. So we put a lot of focus on making sure the managed debugger worked well with the new runtime. Likewise with other features as they come in. So this is very much directed by the feedback we get in the form of bugs, feedback through social media or the forums, whatever it is, that's what's driving this path forward. It's also incremental. So the idea of a .NET upgrade in Unity is a very large thing, and we obviously can't do everything at once. We're trying to, again, be stable and deliver small pieces at a time when they're ready. So what that means is you may be able to, with your application, use the runtime today. We may not have anything working on something you're not using. So for example, maybe something like IPv6 is not working on some platforms. If you're not using IPv6, there's no problem with you using that runtime today. So we're trying to deliver, again, stably features that work across as many platforms as possible and are ready to use, which means you can actually use this runtime. If you are fit in the subset of things we have working and ready to go, they should be stable and ready for you to use. All right, let's talk about what you can actually do today. I've given many talks about this stuff, and it's always forward-looking, but it's so nice to be able to actually say what you can actually do now. So in 2017.1, this was the initial availability of the new scripting runtime. That corresponded to Mono 4.8. At 2017.2, we bumped our Mono version again. So the general idea here is that we're not going to fall behind. That is our hope. We may not upgrade the Mono version every release, but the plan is that we would upgrade in a reasonable amount of time so that future sort of upgrades would not be a shock to the system like this one is. So we are tracking Mono and all their development and ensuring that as new stable versions come out, we can adopt those into Unity. As I said before, a lot of feedback was related to managed debugging. We spent a lot of time focused on to make sure the managed debugger worked with the different clients that are possible for debugging Unity. And we also focused on stability. So of course, any crash bugs coming in or anything like that, we spend a lot of time to make sure that those are resolved first. As far as what's going into 2017.3, that's somewhat unknown at this point. We have some things we're working on that I'll touch on later. But as I mentioned before, basically things are rolling in when they're ready. So when something happens, it'll be available, and you'll just see that incrementally over the next couple releases. So what do you get with the new runtime? When you opt in this switch, you get new C# language features, which we'll touch in a second, and you get a new runtime and class libraries. And there's sort of innumerable things to mention. It's basically 7 years of bug fixes to the open source Mono project, right, that we hadn't had before, and now they're in there. Of course, there might be new bugs in there, but the general idea is that the quality has improved over the past 7 years. You also get compatibility. So these, I was saying before, these new libraries that are using .NET 4 features or C# 6 or whatever it may be, you can now consume those in a Unity project and use those directly. So we're going to do a little example here. There's a lot of coding today. So in my demos, so I downloaded Note-A-Time. Note-A-Time is a time zone and date library by John Skeet of Stack Overflow fame. And we have some DLLs in here. And this Note-A-Time DLL is a .NET 4.6 DLL. So I'm just going to copy this into a project I have set up here. And I don't have it launched yet. So what's going to happen by default if you start dragging in .NET 4 libraries is you're going to get this nice little warning down here on the inspector. And I can barely read it, so I know you can't read it, but it says plugin targets .NET 4.x and is marked as compatible with the editor. The editor can only use assemblies targeting 3.5 or lower. So here's how we enable the magic. We go up to our player settings. And again, this is a per project player setting, so this is included in source control. So if you have a team working, someone opts the project to be upgraded to the new one, someone else is using it. This is not set on your install level or your machine level. This is per project. So right here we have scripting runtime version. We can pick experimental, .NET 4.6 equivalent. You will be asked to restart the editor because this affects the editor and all players. So this is across the board for the project. You can't use .NET 4.6 in the editor and 3.5 in one of your players. So we'll restart. And now when we click on it, we don't have that little red error anymore. So we've actually imported this DLL. I'm going to actually copy over a little script to use it. He refreshes. And if we look at this guy real quick, what you can see is it's just getting the current time, essentially, this instant now. I'm going to put that into our current time zone here, US Central, and then I'm just going to print out what that time value is. So let me just attach the script to our camera. And if we hit play, it just works as expected. So we have the current date and time output to the console. A lot of the exciting things about working on runtimes is compilers, they just work as expected. So, all right, let's go back here. All right, the next thing we're going to talk about is C# language features. So these, again, what I just showed you is available today. In 2017.1 onward, you can do what I just did, and we're going to talk about C# language features you can also use in 2017.1 onward. So I'm going to go through all the features that basically you have now that you didn't have before. I'm going to hit them pretty quick. You can easily go online and check some of these out. And then some of them have special meaning in Unity, so we're going to take a look at those a little bit deeper. So the first thing you have is auto property initializers. This is the new syntax right here. What you can do is declare an auto property, a get and a set, and assign it a default value. If you want to see how this used to look, you would have to do like value 2 down here. You would need a backing field to assign the value to, and then you'd have to implement the get and set yourself. It's also equivalent to declaring, again, auto properties and then initializing it in a constructor. But this allows you to basically declare your auto property, what accessors get and set, and the default value all in one line. Another feature is caller information. So what happens here is there's these special attributes, caller member name, caller file path, and caller line number. Those are replaced by the C# compiler at compile time with who called this method. So you'll see there's default values here, and what the compiler will do if you don't pass them is insert those values for you. So let's take a look at this one real quick to see what it does. Okay, and in our game object, I have all these examples, so let's look at caller information. Again, if we run this one. What you'll see in the output, as I said, starting things up, and then the second line here is not actually our call stack that we usually put in your info, but it's the output from that line that the compiler injected. So the big distinction here is normally, so if you click on this, you'll see this little call stack down here. It's kind of hard to read, but the call stack going up, calculated at runtime, actually matches the info that was put there at compile time. So the distinction is information put in who called what at compile time versus at runtime. And you just get one call frame above, not the entire call stack. This might be useful in places where you're not shipping debug info, for example. If there's a place you want to track something down and see who called what, you could put this in, and without the debug symbol files, you would still get file and line number information, for example. All right, let's keep going through here. We'll skip these guys. There's a new dictionary initializer syntax. So this is the new syntax here. Previously, you had these key value pairs that you had to put in. Now you can use this bracket syntax and assignment syntax. There's something called expression-bodied members. So what that means is when you define a property or a method, you can do it in terms of an expression. So again, here's the new syntax. I have a property name, which is a string that only has a getter. So in C#6, you can only do this for get-only properties. You can't have a setter. And that is equivalent to, if you wrote it out, a get accessor and then said return this value. It's not quite equivalent to this, to using the auto property initializer. Does anybody want to think about that for a second? So the difference is going to be that these are evaluated every time you request the property, whereas this one only is evaluated once on assignment. So if you had like a counter or you were reading something live, name and name2 would get that new value every time you called it, whereas name3 gets the value on assignment and then it's returning a static string every time. Similar for methods, you can define a method in terms of an expression. So instead of the curly braces and writing this out, you can just do the the arrow syntax there and write an expression that you want to be the body of your method. Name of operator, this is a small one but useful. So anytime you want to stringify one of your members, so a parameter name or a method name or something like that, say in the case of an argument null exception, previously you would have to have put, the actual name of the parameter here, right? And then you do something later and you rename that, and your tool may or may not tell you, hey, you're also using this name here. Using this name of, if I go to change this to, and I change it in my code, what I actually get is a compiler error. Oh, of course, okay. Thank you. All right, so if we do that, if we had called a parameter, you're going to get a compile time error rather than just at runtime an exception that tells you the wrong information. All right, so we're back. Let's look at null conditional operators. There's two null conditional operators. One's the null propagation operator, and one's the no coalescing operator. So here, the first one is we have this log name, and we have this nameable class that just happens to have a name on it, and we could pass in a null or an actual instance. If you do this s question mark dot syntax, you can also do s question mark indexer for something that has an indexer. That is equivalent to essentially a ternary operator inline. So it's not like an if-else, but it's an inline expression chooser. So you can say if s is null, just return null. Otherwise, basically propagate my expression, continue down the path. So it'll actually evaluate s.name here. In this case, we have the other operator, where it checks basically for null. And in that case, it says if it's null, return null. Otherwise, return this thing on the right side. So instead of continuing evaluating an expression, you give it a value and say, please return this instead. Of course, this brings up an interesting topic. So if anybody looks at this, I just put you on another slide that this top line here should be equivalent to this, except, of course, in Unity, it's not going to be. So let's go back and see why that is. So if we run, what we get the first time is output null. The second time, we get an error from Unity. And the reason that is in the editor, we have the fake null concept. So we'll go back here. And what you see is we instantiated a game object, and then we destroyed it immediately, which means we have detached the native representation from the managed representation of our game object. And we override the equality operator in Unity to return null in that case. So when you write it out this way, it actually uses our overrided null, our equality operator to check for null and behaves as Unity has behaved in the past. When you use this new operator, it doesn't actually emit a check using the equality operator. It just checks basically reference equality to null. Is the pointer to this managed memory null or not? So you're going to get different behavior there. This has been brought up on the forums and something we're discussing about what to do this behavior going forward, but just note that you are actually going to get different behavior with Unity objects in the editor when they've been destroyed. So we talked about auto property initializers. We're going to talk about read-only auto properties. In that case, you can just define a getter, but give it a value here. So previously, you would do something like this. You would define a get and a private set and set the value. You could also do a backing field and do this here, but this is a little bit different. So the difference here is that in the value case, the new syntax, I can still assign a different value if I want to. So there's essentially a compiler-generated private set. Whereas in the case of value 2, since I've specified what accessors I want, I'm going to get a compiler error because there is no set available to you. So value and value 3 are equivalent. Value 2 is not quite equivalent to the others. Static imports. This allows you to use static methods off of types by putting this using statement at the top. So rather than debug.log throughout your code, you can say using static unityengine.debug, and then it'll resolve any calls to log in the scope of that for the file. And finally, the easy ones here, we have string interpolation. And this right here is the new syntax. You prefix a string literal with a $, and then you can actually put the expressions you want to evaluate inline in the string in the curly braces rather than following the string as arguments. And it doesn't need to be simple values, so you can actually write expressions in here. You can write complex, expressions that actually get evaluated inside the string. Anything you could put later can also go inside of there. All right, so let's talk about some more interesting things. The first one is, let's talk about covariance and contravariance of generic interfaces and generic delegates. So this is a compiler feature, but also requires runtime extensions. So when we use generics and they have a generic argument, sometimes it's intuitive that we put a relationship between that generic argument and maybe something else in its inheritance chain. And covariance handles that in one direction. So we have a delegate here called retrieve. This delegate takes no arguments, and all it does is return a value. I'm going to declare a delegate that returns a base. I'm going to call that retrieve base. And then I'm going to declare a delegate called retrieve derived, and that returns derived. So these are two different types of delegate. One is a retrieve base, and one is a retrieve derived. We then have a method that expects a delegate of retrieve base. If we pass in the retrieve base, everything's fine. If I remove this out keyword, that indicates that we want covariance to happen, and I save, what we're going to get is a compiler error, because these two types cannot be converted. We can't convert a retrieve base to a retrieve derived. And the reason you can't do that is because bad things might happen in general, generics, right? If you, for example, if this was expecting a retrieve base and you passed in a list of retrieve derived, bad things could happen when you're basically taking the values or assigning values into there. Because we expected that we had a list of the derived class and then someone started assigning derived bases in there. So what this is doing is this out parameter is saying that I'm only going to retrieve values out of this generic delegate. And it makes sense. So this delegate is returning us a value, and what the contract here is saying is the thing I return has to be of type base. And if you think about it, anything derived from base is also of type base. So in the case that we're only returning values out, either as return values or as out parameters, it's okay to essentially substitute a more derived type for a more a base type. So this compiles correctly and runs fine. Then we have contravariance after this. So the way to remember this is if you do something like this to indicate your inheritance chain, you have derived to base. The arrow is going from the derived class to the base class. Covariance is when you're going in the same direction. So when you want to substitute a more derived thing for a base thing as a generic argument, that's covariance. Contravariance is when you're going in the opposite direction. So when you want to use a generic with a base type parameter, or base type argument rather than a derived type argument. We'll take a look at that. So in this case, I have a class called base, and I have a class called derived again. Base just has a single field name. The derived has an additional field called description. I create one of these instances of derived and set both those values. And then I have another delegate in this case called stringify. And in this case, it's going to take a value and return me a string representation of what I pass in. So again, now there's this in keyword. Before it was the out keyword. If I remove this and try to compile, what you're going to see is our example gives us a compiler error again. And what happens in this case is I'm defining a delegate that takes the derived, and basically concatenates the name and the description into a string representation. And then we have a base version that just accesses the name. So all it can do is access the name. It doesn't know anything about any derived types. It's expecting a base parameter. So when we pass this into our stringify and log, we're expecting a stringify that will use derived types, and then we pass in a derived item. We pass in the derived one, that obviously makes sense. But now we want to pass in a delegate whose generic argument is a base type. And this one gets a little more hard to think about, because you think, why would I be able to substitute a base where the more derived type is? And what this is actually indicating with the in is these are the values that you are receiving. So in this case, the base in this delegate is what this delegate type is trying to receive. It's saying, I at least need a base to be passed into me. Similar to before, it was saying what it was going to pass out. In this case, the contract is, I need a base. So where a derived class is specified, this is saying, I'm going to always give whoever I call back on a derived type, that will satisfy the constraint that it's at least a base type for the base type expecting delegate. So that's all kind of hard to understand. So let's see where this is actually useful. The biggest place this is useful is in collections, and it's used heavily in IEnumerable. So if we go to the definition for IEnumerable, what you'll see is that is actually an out parameter. So it is covariant. And if we go to this guy as well, you'll see that one's also out. So essentially what this is saying is it allows you to pass collections of more derived types into methods that are expecting collections of less derived types. So in this case, I want an IEnumerable of base, and I just want to print out the name. It makes sense that I should be able to pass in a collection of derived types into that method, and it can iterate them and print out the names. All right, and the last one, async await. Okay. So this one's a little bit meatier. I also want to say that some of these features, since we are in the same boat as you guys with these developing on a more older version of the runtime and class libraries compilers, we have not used these features extensively ourselves either, right? So we haven't necessarily formulated the best practices for all of these things within the Unity environment. And async and await is one of the ones we get asked about a lot, especially in relation to coroutines, because it's very similar in the idea of essentially async execution. So what we're going to see here is in our start, I'm logging some messages, and I'm also going to capture the thread ID of everything we're doing. So we come into start, and I do start1, the current thread ID, and then we're going to call this sumAsync method, and we're going to pass in a collection of integers. And then when that's done, we're going to log something out to the console again. Before we look at sumAsync, let's look at sum. So sum is just a regular C# method. It takes a collection of items. We're going to do some more logging. We're going to iterate those items. We're going to sleep, since this is a threading example, to give us a little bit of time to see something interesting. And then the sumAsync method calls into sum to actually do the work. The special thing here is that this sumAsync does this await on a task.run. So what's going to happen here, as we walk through this, we're going to come in on the normal Unity lifecycle of a mono behavior and call the start message. You're going to see start1 thread logged to the console. We're then going to call sumAsync. It's going to come in here and log sum1. This is still occurring on that main thread. And then this await task.run is going to occur. And that's going to start running on a different thread, and that's going to yield control to similar how you would in a coroutine. And that yield of control is going to return actually up to the start method. And then what we're going to see next printed is start2 on this main thread. So the total has not yet been returned, and anything after that has not been executed. So this is actually awaiting the work to happen on the other thread, but it's return control flow on the main thread back to where our caller was. And then what we'll see is this sum1, sum2, and sum3 is going to occur. And if you look at in the console, it's going to be on a background thread ID. So we wrote the thread IDs. It's not the same thread ID. But then once we resume, part of the async and await system is, what do you want to do when the task is done? How should I complete everything that occurs after that? And what you want to do in many UI systems is return back to the original calling thread. So in the case of Unity, we supply a default sync context. That's what gets captured here. And that captures the information of, when I'm done running this task, how do I return from this await, and what do I do? So we will, as part of our update loop, process any of these async tasks that have run, and they will call you back actually on the main thread. So you will see this sumAsync total 2 is the total there, and then you'll see the thread again is back on the main thread ID. So let's take a look at that. Oops. Again, it's probably hard to see here. But what we have is what we said. We have the start. We go to the sumAsync. It begins, returns control flow to the start. Start ends. Work happens on the background thread, as we can see here. That finishes up, and then at the very end here, it finishes the rest of the sumAsync on the main thread. So main thread disappears 1, 31 was the background thread, and then we resume control flow back onto the main thread. Again, the key takeaway here, I would say, is that we don't have plans for async and await to replace coroutines. That's for a couple different reasons. They seem to have slightly different purposes. Async and await also has some overhead as far as allocations that coroutines don't have today. They are working in sort of newer versions of .NET on a value task, which would avoid allocating when doing this task routines. But today, essentially, we don't see them as a drop-in replacement for coroutines. All right, I think that's all those examples. All right, so everything I've gone over is stuff available to you today. From 2017.1 onward, you can use that, you flip that switch, and everything I've talked about is available to use right now. So let's talk a little about things that are available in the future, coming down the pipe. So since we were just on the language discussion, let's just go forward with that again, and let's talk about C#7. So what I want to do is spend most of our time on one feature of C#7, and that's ref returns and ref locals. So if we look at this little example, all we're doing is initializing an array of vector2. I've defined a vector2 as a simple structure having an x and a y and a toString method. I put 2 items in there, which initializes them to 0 by default. I then iterate that array, setting the x value to 0 and 1. And then we iterate that array and print out all the values. So if we run this real quick. What we see is we get 0, 0, and 1, 0, which is the values that we expect. All right, so now, instead of an array, Let's do this in a list. So we're going to create a new generic list of integers, and we're just going to initialize it with our values array. Let's say that. And I'm just going to try to do the same thing. This is a vector 2. And I'm going to iterate my value list and say I want to update the y values. And what we get is this compiler error saying, cannot modify the result value of the list because this is not a variable. And what's happening here is the list has an indexer, and you can retrieve values using the bracket syntax, but it actually makes a copy of value types. So arrays in .NET have always had ref return conventions. So when you index something on an array that's a value type and you say dot, you can assign right to that, and it's actually assigning to the element in the array. In the case of lists or any other user-defined collections that return value types, it's actually making a copy and not doing what you would expect. And that's what this compiler error is about. So let's go about fixing this. Let me just comment this out. So we're going to have a class, and let's call this vector2refList. Right? And I'll just take a vector2 and say an list of those guys. Right? And then I need an array of them to hold the items in. And I'm also going to have a count because we might have less items than the capacity of our array. So we'll just use a little link magic here. And okay, so we have our list class. It stores our items in an array and has a count. We pass in an ilist of vector2s. We're going to copy those in. So let's expose a public int count. And let's use this using our fancy new syntax here. So we can just kill that. And the last thing we need is an indexer. So the previous way you'd write an indexer is you would say vector2, this, int I for the actual index value, and then you would write a get. And you would say return items, bracket I, right? You might do some bounds checking or something like that, but this is what you would return. So let's try our vector2 list in place. So instead of a list, I'm going to use a vector2 list. Don't make this generic. I'm going to pass in the same collection, and I get the same compiler error. So I try to iterate this, and it says the return value type is not a variable. So we didn't use our ref returns yet. So the trick is, you can come here, instead of returning a vector2, I can return a ref vector2. And then instead of items, I can return ref items. And what that's doing is returning a reference to the actual item inside of that array. Now, our compiler is happy. And what we'll see, let's just multiply this by 10 or something to make it a little more interesting. Our value list is what we want to output. Oops, count. And we get our output. So the output from the array is still 0, 0, 1, 0, but we see 0, 0, 1, 10. So we've actually modified the contents of our own collection via reference. So let's take this exercise a little bit further. So let's copy this guy. Let's call this native list, right? Instead of storing items here, int pointer, right? Let's do that. And then what I'm going to do we'll say items.count, times marshall.sizeof. So we're getting the native size of our vector2. So we're allocating native memory now, not managed memory for our structure. And then we need to set our count. We're going to set that also to items.count. And then we need to copy the values over. So we're going to have to do something like for var I. We might do something like a mem copy, obviously, but in this case, we'll do okay, so we want to copy into memory, sorry, structure to pointer. So we are going to pass in our items I, and let's see what that is. The items plus I, and then let's copy this size out here to reuse this. So this is doing pointer arithmetic for us and offsetting. So we're going to be writing into native memory the contents of the array that we got passed into us. All right, so that should do that. We've got our size set up. And then now we have this error because it's saying I don't know what items is. So what we're going to do, since we have a pointer to native memory, is we can just say that this is a vector 2 of items. And since we're using pointers, that needs to be unsafe. And now we can use our vector native list. So let's do that. Okay, we're going to edit the native list, and let's set these values to say something bigger. Again, it'll be 200. And then we're going to loop all the items in our native list, and we're going to write them out. The other thing to notice when you're doing a ref return is you only need to define a getter, because that allows you to set and get the same value. So you can't define a setter when you're doing a ref return on an indexer. So now that we've built this, oops, let me write out the value native list. And then we will run without debugging. And what you see is we have the same behavior. So we've allocated native memory. We're using it for value types, and we get the same accessor syntax as you would with a regular managed array. The last thing we would probably want to do is something like add disposable here. And then we would say something like Marshall free H global, the items, right? And then we would put that all in a using up here. And if we run again, yeah, we get the same value. So what we've done is essentially very close to the native array that Joachim talked about in his job system talk. And this is sort of how it happens. And that's why ref returns are one of the key values in supporting something like that. So you have a nice syntax for accessing native memory in managed code in a type-safe way with a nice syntax of the indexer. All right. Another topic is net standard. How many have heard of net standard? Raise their hand. Okay, about half of you. So there are a lot of blog posts coming out of Microsoft about this. It's a large topic, and I referenced one here. This was an introduction to it, and it's actually really good. It's quite a long one. There's lots of things to scroll through, but it gives a good background on what is .NET Standard, why it exists, and sort of information on how to use it. But I'll give you the short version here. I took these images from that presentation. And what happened in the past was that you had the .NET Framework first, right? And when you think of the .NET Framework, what you think of is .NET 3.5 or .NET 2.0 or .NET 4.6. You think of the class library API surface, right? What types can I use? What methods can I call? Then came along Xamarin, which came out of the open source Mono project, and they've defined their own class libraries as well for some of their products. So Xamarin iOS or OS X or Android, they actually have a different class library API surface than the full .NET profile. And then .NET Core came out, and they have a completely different API surface for their base class library. The important thing to remember when you're talking about API surface is it's not just a type and a method, it's actually the assembly. Everything in .NET is assembly qualified names. So it's not just, do you have system object and it has toString? It's what assembly does that live in? And that needs to be coherent at 2 different times, at compile time and at runtime. When you're compiling something and you have multiple assemblies coming together, they all need to agree on where these types live. Same thing when you're running. They all need to agree on where they live, or else they're actually distinct types. And you're going to get errors like you may already have system object, and you're going to compiler error saying you don't have system object, or you have 2 system objects. So at compile time and at runtime, there needs to be a coherent vision of where all the types are and the surface they expose. Since we're here at Unite and we're migrating to .NET, obviously we also add to this picture. Previously we had a .NET 2.0 and a .NET 2.0 subset profile. We are going forward offering the .NET 4.6 profile, the full profile for compatibility reasons, and then we also are defining our own smaller subset as well, which will likely correspond very closely to Net Standard 2, if not be Net Standard 2. So the idea here is that there would be a .NET Standard library, and the goal here isn't that all these different vendors had only these APIs, or they would be limited. It is a lowest common denominator, but it's fairly large at .NET Standard 2. I forget how many APIs are there, I think around 40-something thousand. But what that means is that you, as a library author, can write code that will run across all the .NET ecosystem. And there was efforts of that in the past, but this is sort of a much better way going forward. And what that means in Unity is we want to be able to consume these libraries in Unity projects. And again, this is mainly about compatibility. So if you start looking online or on GitHub or something, or you're pulling down binaries, a lot of them are going to be targeting .NET Standard or PCLs in a previous form, portable class libraries, which was an initial temp at this. And we want those to be able to work in Unity. All right, so let's take a look at our Node-a-Time demo again. So if I look in the Node-a-Time that I downloaded, they have this additional folder called Portable. So if I do monodis, this is the mono disassembler, and I do that on node-a-time.dll. What you'll see at the top here is these are the assemblies that this assembly references. So it references MS Corelib, System XML, System Numeric, standard stuff that you'd expect to find in the .NET framework. If I run this on the portable one, you're going to see assemblies that you might not be familiar with. You're going to see something like System Runtime or System Diagnostics Debug. And what happened was, through the PCLs and through .NET Core, they broke things down into much smaller assemblies. So instead of all of them as corelib, there's very specific assemblies with specific tasks. So what we want to do is we want to use this library, because going forward, people are using, again, .NET Standard and portable libraries. So we're going to copy this guy, the portable DLL, into our example. And let me switch the editor back. And we start to get a bunch of errors. And I'll read some of these errors. It's basically saying system IEquatable is defined in an assembly that's not referenced, considering it a reference to system runtime. So it's that runtime we talked about. System runtime is sort of the small library that contains a lot of the stuff that was in MS Corelib before. So core types would be in system runtime, and it's saying we don't have that. And that makes sense because the assembly we want to use references this assembly, and by default, the .NET Framework doesn't have that. So what we can do is we can go back to our player settings. We're going to look into how this works in a little bit more detail in a second. But what essentially this says is compatibility shims, or facades. There's 2 different purposes. One is for compile time, one is for runtime. But it's basically an assembly that just forwards requests for one assembly to another one. Unfortunately, there's a lot of these. So I made this as an option right now. This hasn't actually come out. Again, this is in the future. This is what we're trying. But when you click this option, what we're going to do is we're going to add all those assemblies to your compilation step when you're rebuilding your code. And what that means is if you did reference something like system runtime, that DLL that we referenced, there's a system runtime.dll, it's actually empty. It doesn't have any implementation. All it does is say when you're looking for system object or system IEquatable, it's actually in MS Corelib in the target framework you're running on. So we changed that. We can go back here. We can just re-import this right now. That reruns our compile, and everything's happy again. So just so you can see, let's take a look at this guy real quick. Let's put an error in here. Save this. And then let's look at our editor log. So what you'll see is we got our compiler, we put the error in there, but you can see all the assemblies we're referencing. So you can see all these assemblies are needed to forward all these requested types to the actual implementation underlying that. So again, at this point we made it an option, partly because it may affect compile times. We're still investigating that. The other thing is it may lead to incompatibilities. So we're actually referencing all these assemblies for you. Things that people have done in the past is they might have taken suppose you wanted to use system data. You might have taken a system data from somewhere, likely from Mono, and dropped it into your assets folder. Once you do that, if we start referencing that for you, you're going to get an error saying system data was already defined, because it's actually in your assets folder as an assembly, and it's being pulled out of the actual base class library. You don't want to put assemblies from the base class libraries into your assets folder. I know people have done that in the past, but that is generally not a good idea. The best way to do that in the near term is there's response files you can drop in your assets folder. That's essentially additional command line arguments for the compiler. Just add -r:system data, and that'll pick up the right system data. Because when you drop one in the assets folder, you're getting a particular one. When you reference it there, you're getting the actual one for the framework you're targeting. So .NET 2.0, .NET 2.0 subset, .NET 4.6, and then our new subset all have different actual versions of system data. You want to pick up the one that corresponds to the framework you are actually targeting. All right, so we have a few more seconds here. What I wanted to do was just show you a little bit how this net standard stuff works at the command line, so we can see what's actually going on behind the scenes. So what I'm going to do is use the Mono compiler. I'm going to give it no standard lib, which says don't reference MS core lib for me. I'm also going to say no config, which says don't pick up the default file for the compiler specifying what to reference, because it references assemblies for you. And then I'm going to take this and try to compile class 1. And what it says is it can't find all the standard stuff in MS core lib. If we look at class 1 real quick, I forgot to do that. There's nothing here. It's just a class as a string. But what we see is it doesn't know where to find all these normal types. So what we could do in the normal world is we would add a reference to MS core lib, and that would satisfy this. But what we want to do is we want to build a net standard version of this library. So real quick, I'm going to say T library, because we actually want a library folder. And then I'm going to say -r, and I just happen to have net standard sitting here. So there's this ref folder, and there's all the different versions there, but I want to build against 2.0. With the net standard, the general idea is you build against the lowest version you need, but we're going to use 2.0 here at this point. The one thing 2.0 did was also put all the assemblies back together. So we just saw system runtime, system XML, all this stuff. If we look in this directory, there's a single one. So everything that's supported by the net standard 2.0 profile is actually in a single net standard DLL, and that's all you need to reference. So if we build this now, that succeeded. We now have a class 1 DLL. I'm going to run monodis on class 1 DLL. And what you'll see is all this assembly references, there's the actual assembly itself called class 1, but above that, what it references is net standard. So everything this needs from the base class library goes through the net standard. So the normal types are there, system object, equatable, the stuff we saw before. But remember, it's assembly prefix. So what it's saying is when it needs to find that stuff, it's going to look for net standard. All right, so real quick here, let's do another compile. So I'm going to look at program.cs, and all this is going to do, let's just take these guys here. So I just want to reference class 1 from a program. So I'm going to do MCS, no standard lib again, no config again. Oops. I'm going to compile program.cs. Okay, so it doesn't have any of those types. But for our program, I want to target the .NET framework, because I know that's what I'm targeting. So we don't need to target net standard in this case. So I'm going to add a reference to a Mono implementation. Okay, so I'm referencing the MS core lib from the Mono profile that we are running against. And it says I don't know what class name is. So we didn't add a reference for the DLL we just built. I'm going to add a reference to class 1. And now we get this weird error, so let's do that again. System object is defined in assembly that is not referenced. So we already have system object on the command line from MS core lib, but now we're referencing class 1, remember, which was compiled against net standard, and it's saying you have a system object in MS core lib, but I'm looking for system object in netstandard.dll. So what we need to do, we're going to take a look here at under the Mono directory, there is a facades directory. And so before, there's, again, two different cases when you're doing this. One is you need a unified view when you're compiling of where things are going to be. The other is when you're running. So in this case, what we want to do is reference this DLL. And what this one's going to do, since we actually know we're targeting the .NET framework, is this facades DLL for net standard. Let's go down here and see. What this is just type forwarders. So what this is saying is, anytime you need net standard and you're looking for system action, for example, it has this .assembly extern. It's saying basically go look in assembly MS core lib instead. And what that means is the compiler's going to be happy because class 1 needs these type from net standard. It's going to point to them in MS core lib. We're compiling program.cs. It's compiling against MS core lib as well. And both of them think that, OK, once I resolve everything down, system object lives in MS core lib. Okay, so now we go to program.exe, and we can run it, and just outputs the name of the class. So we can basically have a .NET framework target executable. This corresponds largely to what you're going to see in Unity, consuming a .NET standard library. And we explicitly specified the net standard DLL here, but in the Unity case, we can reference the net standard DLL for you, but we also need to reference all the other DLLs if you're using a net standard version prior to 2.0. Demo. A couple things we're working on in the future. We have an AutoCP debugger underway. So we are trying to share code as much as possible between Mono and AutoCP implementations. The debugger actually works over a socket protocol. So once we actually have this working in the AutoCP runtime itself, the existing IDEs will just work. They connect to the debugger over the network, and that means you're debugging in Visual Studio or VS Code or whatever you do will work with AutoCP players just as well as they do with Mono today. We're also working on adding TLS 1.2 support to our class libraries. That'll give you secure network communications. We're also making sure that when we can, we will access the system certificates available so that it'll work out of the box. So when you do a web request and you hit google.com with HTTPS, it'll authenticate that and return you what you're expecting. A little more detail, I said on the debugger, we're trying to reuse as much as possible. Internally, we are trying to unify essentially our different Mono versions, this new Mono version, our AutoCP code base, as well as our Unity code base. So right now, these different scripting runtimes have their own way of talking to, for example, the file system. The Unity engine does as well. We're trying to isolate into a single library that all will use. And that's just useful for bug fixing or handling special cases that all the different runtimes, the Unity engine will all be within the same layer. We're also unifying AutoCP and Mono. So they're the class libraries themselves. We've always used the Mono class libraries as is on AutoCPP. We are unifying the debugger, as I said, that's happening right now. We also share the exact same GC between the two. So this is the older BOEM GC that we're still using, but any GC work we want to share so that Mono and AutoCPP will behave the same. And on the topic of garbage collector, it's still important. The big issue here is that any sort of modern garbage collecting algorithm requires many more constraints on the Unity engine itself. So we are intimately aware of the behavior of the Mono runtime, and we also take advantage of that for performance optimizations in the Unity runtime. So we access managed memory directly on the native side, and with any modern garbage collector, there's restrictions around that. So you need to inform the GC before you're about to write to memory, or you may need to inform it after you've written it so the GC can do some bookkeeping. We do have that internal refactoring underway so that we don't necessarily started the work on integrating a new GC, but the work on the Unity side to make that even possible is moving forward. All right, that's it. We have time for a few questions. If you have questions, please use the mic in the middle aisle.
Good talk. Could we expect the C# 7 features when the job system is released? If you mentioned that's...
We are trying very hard to make that happen, yeah. That would make the syntax locks easier. We're still working out how to make that possible and fall back without it, but that's the intention.
Cool. And second question, are there any plans to bring in like NuGet support or package managers for DLLs?
Yeah, we are discussing the best way to do that with Microsoft representatives right now, the best way to integrate NuGet.
Sweet. Thank you.
Anyone else? All right. Thank you very much.